Hello. All right. Today we're going to cover pneumatic systems just a little bit and thermal. So I don't know. Anyone take a look at homework 3 yet? Oh, you did? There's no pneumatics on it. There is hydraulic, not pneumatics. Um, so I'm just going to go over this because it is helpful, especially if you're designing anything with pneumatics, knowing how this works. A lot of the equations look similar to hydraulic. But we are definitely working with compressible systems. So it's pretty complex. There's a lot more nonlinearities. We're going to talk about some of those in the next couple of slides. And because these are compressible, we want to look at the mass flow rate, because volume flow rate, if I'm just looking at volumetric flow, it might not give me the full picture, right? Because density can change depending on the pressure. So we're going to look at the mass flow rate. And if my density changes, it looks like this complicated equation where we're looking at density and volume changing as a function of time. The other thing that makes it more difficult than hydraulic systems is thermodynamic effects. So, this equation, we have, a relationship between pressure, density, temperature, ideal gas law. So the higher the temperature, the more pressure I'm going to have, right? The gases are much more affected by what that temperature is. So that's kind of what we're looking at today. Hi, good morning. So this is not updating for me. Here we go. No. Okay. So for pneumatics, now we covered hydraulics last time. Every time I have a pipe, a valve, something like that, it gives me resistance. So the fluid has to, like, there's some energy loss as it goes from one point to the other. So for most, and I would say for all of our pneumatic problems, flow through the valves is going to be turbulent, compressible, and complex. There's two different types of conditions. So we're going to talk about those two: choked versus unchoked flow at the minimum area. So if we have some kind of throat valve, whatever, we'll talk about those two things. But let's look at this diagram, for example. Mass flow rate is a function of these two pressures. So we're talking about upstream pressure 1, downstream pressure 2. Which pressure is higher? Which pressure is higher? It's always got to go from high pressure to low pressure. So P1 is greater than P2. There's a throat area and there's a temperature. So temperature is also going to affect that mass flow rate. So we're looking at M dot, and there's two conditions which I'll show on the next slide. Depending on what that difference in pressure is, the more of a difference, the higher P1 is compared to P2, it's going to flow differently. Whereas if they're closer to each other, the flow is going to change. So we've got two different equations, and it looks like this. Don't these look like nice equations? Wouldn't you like to write these equations down? So again, pneumatics is a lot more, as you can see from these equations, nonlinear, right? I've got this square root going on here, and I have two conditions. Let's talk about them. If the flow is not choked, or if the flow is choked, what's the difference between those? Well, if I'm looking at P2 over P1, this is downstream pressure over upstream pressure. If this is greater than the critical pressure ratio, that gives us a choke condition. Well, what's the critical pressure ratio? That equation is over here, which I don't know if you remember ever working with this, but to figure out that fluid flow, I need to figure out what is the specific heat of this gas. So for example, for air, the critical pressure ratio is 0.528, but for any other gas, it could be slightly different. And you can look these up, engineering toolbox, whatever. I have my critical pressure ratio. So if P2 over P1 is greater than 0.52, which means the downstream pressure is like 53% or higher of the P1 value, I get this very nonlinear relationship. There's more swirls. It's not choked. It's those two pressures are pretty similar. It's only like a 50% drop. But if P2 over P1 is less than the critical pressure ratio or equal, then I see more of a difference. And so it's 50% or less. And so at that point, I actually get a pretty nice constant flow. You see the equation, if the temperature is constant, this actually just becomes a constant value. And so my mass flow rate is constant. It's choked flow. And I'll give you some graphs here that kind of help with this. But everything comes down to the critical pressure ratio. Is a lot of times we'll kind of see based on some example graphs, but I should model my system with both of these. Like what happens if it's our delta P is not that different compared to what happens if they're very different. We're going to see two different types of flow rates. And so that's kind of the difference between choked and unchoked. Here's a, come on, update. Here's a pretty good graph right here. So on the x-axis, this is the input pressure. And then this is our mass flow rate on the y-axis. So again, we're using this, let's just say, this is our input pressure. Downstream pressure is atmospheric pressure. And so at the beginning, if my upstream pressure is basically the same here, I don't really have any mass flow rate. Does that make sense? They're both the same atmospheric pressure. Nothing's going to flow. As I increase that upstream pressure, that's where we see that nonlinear relationship. So notice it's not a straight line. It's nonlinear. But once I get to the critical pressure ratio, where P2 over P1 is equal to 0.528, this is for air, that's where I change from unchoked flow. This is really swirly. There's not much of a difference pressure-wise, but once I get to that pressure ratio, that's where it's choked. And now, as I increase my upstream pressure, it's a linear relationship. So more pressure just equals more flow. It's a linear, nice equation. Those are the two differences. Now, again, if I were to model a system, I would want to model both of those. Obviously, this equation is a lot more complicated. It's got a large square root, as you saw from the last slide, right? Some of you, yeah. So those are the two different cases. Another way I can look at it is having a hard time updating. Another way we can look at it is the pressure ratio. So if I'm looking at pressure ratio versus mass flow rate is going to stay constant if the pressure ratio is less than the critical pressure ratio, 0.528. So on the left-hand side, this is choked flow. So it doesn't really matter what the pressures are, as long as my downstream is a lot lower than my upstream. We have choke flow, and then there's a certain point at that critical pressure ratio where we see a nonlinear relationship. So that's, for example, let's say we were able to hook up your water bottle to one of these right here. So we're going to just take someone's water bottle, maybe a metal one. That could probably hold up pretty good. So we got a metal water bottle. I can't talk. And then we're going to hook it up here. And we start to we get the flow rate going, right? So what's going to happen is first, there's going to be a large pressure difference. I'm going from the compressed air into the water bottle, which has just atmospheric pressure, right? And so at first, it's going to be kind of it's going to look like this. we're going to have a nice constant flow rate from upstream to downstream pressure. But as that pressure grows, then there's a point where, okay, now there's not that much of a difference, and so our flow rate becomes nonlinear. It's not as nice. It's swirly. It doesn't want to really push through because there's not that much of a difference. And then ultimately, there's a point where they're equal. So once that water bottle's filled with air, it's all the same pressure. There's no more flow. That's really what this graph is showing. So there's two different cases for pneumatic systems looking at that flow rate. And just for you all to know, it goes. This is the equation. So this is choke flow, linear relationship, not choke or unchoke. This is where, again, we have P2 is not much different than P1. So two different equations. We like this one, it's linear. That'd be nice to just model it this way, but to have a good complete model, we'd have to have both. So we don't get into pneumatics a whole lot. It's very similar to hydraulics. It's just a lot more nonlinear stuff. Temperature is also related. Now, fluid capacitance, we could define as basically change in mass with respect to pressure. This is also if I have a pressure vessel, just like with hydraulics, it's just anything that can store the fluid. In this case, we're talking about a gas. We're not going to deal with isothermal processes or anything like that. We're not going to get that far into it. But I'm going to update. Having a real hard time. And not that, but wow. Is it going to go anywhere? Is this fun? Well, you guys want to look at what's on here? Because I imagine it's just a really bad internet connection, and sometimes it really doesn't like the slides that I want to show. Jeez. All right, forget it. C for a constant volume is equal to B over RT. That's on my next slide, but you can't see it. So the capacitance does change. Obviously, volume plays a big role in it. What is R? Yeah. So for whatever kind of gas we're using, the constant. And then we have our temperature, right? So the more temperature we have, I actually have less capacitance because my gas wants to expand. And so capacitance is equal to B over RT for a fixed volume. And when I post the slides, you'll be able to see that. It's just my presentation doesn't want to show it. All right. So that's, you know what, V equals V over nRT. It's really just based on the ideal gas law. Okay. Now you don't have a homework problem with pneumatic systems. But how we would approach the problem, it's very similar to hydraulic, except instead of looking at flow rate, volumetric flow rate Q, right? Because my gas can change density, I can't just look at volume, I've got to look at mass. And so really it's the conservation of mass. You can look at this as m dot for the control volume. How is the mass changing within that control volume? That's equal to the sum of all the flow rates coming in. And these W's stand for m dots. So I have a mass flow rate coming in minus a mass flow rate leaving. So if I have a pneumatic capacitance and I'm looking for the pressure, we can solve for it using this equation. So That's on the equation sheet. Pressure dot, the change in pressure with respect to time is equal to, notice this is just 1 over capacitance. That thing is flipped, multiplied by the net change, which is sum of inputs minus sum of outputs. And then if I have a changing volume, I've got to include that here. So if I have something just like the pneumatic, we looked at the hydraulic cylinder. If I had a pneumatic cylinder that could also expand, that gives us that equation right there. And it looks pretty similar. So we've got inputs, outputs, change in volume that can change our pressure. Now, this equation does look a lot like the hydraulic one. So this was for a compressible fluid with a volume that can expand. This is a compressible gas with a volume that can expand. So notice they're pretty similar. Temperature does play a role for the gas, whereas it didn't over here. But again, if I have a Q in, or if I just have an input and nothing's leaving that tank, just an input, then I have some kind of input mass flow rate. I could substitute in there. And this mass flow rate, when we talk about choked and unchoked, that's what's going on here. I could have either a choked flow or an unchoked flow, depending on that pressure. And so that's where we would actually take that equation and plug it in, which gets even more complicated, right? Nonlinear, a lot of things going on, temperature plays a role. There's just a lot of factors that you might have to linearize to be able to solve. And that's why we don't focus on it too much. Questions? All right, let's do a quick problem, then we'll move on to thermal, which we do use throughout a good amount of the class. Oh, and you know what? It's not. See if I can go back. There it is. Okay. Now, this schematic is basically what I was talking about with the water bottle. We got Oliver's water bottle, and we connected it to the air, and then I opened the valve. Here's the valve. I am on the right side. This is the water bottle. I have the supply tank, which we would just say is a certain pressure. I'm not going to make a dent in it. It's just going to be a constant pressure. That's like the building air pressure. And then once I open it, mass is going to flow in, the gas is going to flow in until I reach steady state, which means this pressure equals that pressure. So eventually we're going to get to a point where all of the pressures are equal. And we want to create the equation for this chamber. So we're going to use some of those equations that we just talked about. A lot of the again, there's a lot of different variables going on, so these equations get pretty large. But the first step is to breathe. Breathe. Okay, the next step is we're going to try to figure out the order of the system. What do you think the order of the system is? Based on hydraulics, because pneumatics, hydraulics, similar. What would you say the order of the system is? What? 0? 2? Second order? I have 2 tanks, right? I've got a supply tank and I've got a chamber. Now, how many of them is the pressure changing? Just one of them. So really, I'm just going to focus on this one. I really just have one tank with a changing pressure. So this is going to be one first order equation. And we're going to look at P dot. How is the pressure changing in the tank? Because supply pressure is not going to change. It's going to be constant. So really, I'm just going to have one first order equation. Okay, so I'm going to set that up. Just one equation. Body diagram. So, I can create my volume. This is the pressure inside the volume. Here's my valve. Again, this is what we use to show a resistor. So I've got a supply pressure going across the valve. And this is giving me my Wn, or mass flow rate in, m dot. So this tank has capacitance. We've got a supply pressure. Just like with hydraulics, I have a change in pressure. So it's going to go from high pressure to low pressure across a resistor, across a valve, gives me a flow rate. Now, in this case of a gas, I'm not using Q's, I'm using m dot, because density can change as the pressure changes. And so this is our, here I could also look at temperature. So the temperature of the chamber also can affect what's going on equation-wise. Everyone good? Okay, these are just some of the pneumatics basics. Not a major focus of the class, but similar to hydraulics. Input, output. What would you say the input is? What? W in? Yeah, we can do W in. Mass flow rate. That's going to change it, right? What is W in affected by? The tank. It is affected by the tank pressure. I would also say, it's really affected by the supply pressure. The more supply pressure I have, the more that flow is going to be. So those are going to be related. And then output, just like hydraulics, would be, yeah, P, pressure. This is what we're tracking. How much does the pressure change? When is it going to reach steady state based on the dimensions, temperature, so forth? Okay. Now we're going to get to the definitions. I know we haven't covered them much. They look very similar to some of the hydraulic stuff. So for definitions, the first one is very similar to hydraulic. We have a Cp dot, so capacitance times pressure dot, equals, this is going to be the net change in mass. I could write it as m dot, which we could say is the sum of all mass flow rates in minus the sum of all mass flow rates out. And C, capacitance, is equal to V over nRT. Now, I know that I have a mass flow rate in. Is anything leaving? No. So there's nothing leaving, so we can simplify our equation like that. And we talked about choked and unchoked. First, we're going to assume that at time 0, the pressure, downstream pressure divided by the supply pressure, is less than the critical pressure ratio. And so this would give us a choked flow. Basically, it's capped by the area pressure. So we've got Mach 1 conditions. It's going to really flow in very quickly, and it's limited by some of those dimensions. And then later, once this kind of evens out and this becomes greater than critical pressure ratio, that's where we'd be unchoked. And again, if this is just regular air, it's going to be 0.528. That's the ratio where it cuts off. So when air, 0.528. So that's kind of the point for air. If it was a different gas, it would be a different ratio. So, like I talked about before, I'm actually going to create two different equations for this. One of them is going to be somewhat nice. The other one is going to be very nonlinear. That's the unchoked flow. So two different conditions, we're going to put it together. I'm going to go to the next slide, and I'll draw this all out. And there it is. Okay, so first condition is choked. My capacitance I can rewrite as V over nRT times pressure drop. This is equal to M in dot, the mass flow rate coming in. If it is choked, that equation, which I showed a while ago, is equal to this. Now, this is specific heat of the gas. So if I know what that is, I know R and I know the temperature, this just becomes a constant. Now, as that, this is a constant, the supply pressure is a constant, the area is a constant coefficient. So this is just based on the smoothness, basically, of that orifice or whatever that valve is passing through. So all of this, it actually just becomes a nice constant. And so our pressure is going to change. If the volume is constant, temperature is constant, that P dot is directly related to upstream pressure. Okay, so that's a nice constant flow. It all kind of simplifies. However, again, there's a point where once those pressures get somewhat closer, then we get unchoked. And now I get the same equation on the left-hand side, but my right-hand side becomes a lot more complicated. So this becomes, we still have the coefficient of discharge, area, supply pressure, but this is 2 specific heat. And we've got this in brackets. Yeah. Okay. That's kind of a reason why I stay a little bit away from this. Hydraulic, especially if I'm dealing with incompressible, it's pretty nice. I have a linear relationship. Once I get to pneumatics, not only am I seeing a lot more turbulent, it's got to be turbulent, it's a gas, right? But we're also dealing with temperature, we're dealing with all the different gas constants, everything like that. So there's a lot of variables going on here. And as this ratio changes, the closer that they get, this whole equation changes. And so the only way to really use it like a linear differential equation is if I can linearize all these things, or just find where it's like operating at once I hit steady state. So that's just my little lecture on pneumatic. We don't really get into it too much, but if you were to ever see it, I just wanted to show it is somewhat similar to hydraulics in that, I have capacitance, I have a pressure change. I'm looking at sum of input flow minus output flow. We just have two different input flows we can have based on the pressure ratio. How you feeling? Okay? All right. Now I'm going to go to thermal because we do use this quite a bit. Some of you have maybe already had heat transfer or taken it right now. So that we use for other homeworks down the road. We're going to do an activity as well today, class. So we use it more. Let's go on to thermal. And here's our analogies. Nope, it's coming. Maybe. Come on. Maybe if this slide has like too much stuff, it just has a hard time. Oh, I switched away. Here we go. Nope. Come on, go back. It's only delayed by like 30 seconds. No big deal. Here it is. All right. I showed this I think last time in class when we were talking about hydraulic. Thermal is really similar to hydraulic and electrical. A lot of similarities here. I have something flowing. We have heat flow, lowercase q. What is causing the heat to flow? A difference in temperature, high temperature to low temperature, just like pressure, voltage. I have capacitance. I have a way that I can store the energy. Every material has some thermal capacitance, and there's also resistance. There's materials that really resist the flow of heat, right? And so we can model this in a very similar way to hydraulic or even electrical problems, just because we've got similar components and different variables. Okay, so let's look at how we would set that up. You're going to see some of these equations are going to be similar, and these are the equations on the equation sheet. You don't have to memorize anything. It's just for every space, I'm going to set up an equation. So what this equation, and I'll get to the final equation. So I know some of you understand this more than others, but to set up our equation, we're going to use conservation of energy. So for thermal stuff, it's conservation of energy. I have two different ways that I can gain thermal energy. The first is just direct heat flow. So that's lowercase q. So I have some kind of heat just flowing in. There's no fluid or anything for that. It's just heat coming in. I can have heat leaving. But net input enthalpy rate. This is where I do have some sort of fluid coming in with a different temperature. And so we are increasing our thermal, our temperature of our capacitance based on that different flow. And so our equation handles both of these. This is related to some kind of mass flowing in. If there's no mass flowing in, it's just purely based on Q. What's my input heat? What are my output heat flows? So we'll get to our equation, but those are the two different types. So sometimes I can cross off some of them. Usually I have some type of Q, but not always do I have a mass flow rate coming into my space. We just need to define, and the problems typically come as what is our boundary? Inside of there, this is my capacitance. So whatever that material is has some thermal capacitance. Volume plays a role as well. You don't need to write this down. It didn't even update, so whatever. Nope. We'll just skip it. Good. In general, just like with uh, a lot of real systems, they're nonlinear, they're distributed. When I think about temperature, think about the wall right there. Is that wall all the same temperature throughout the wall? Even if I'm looking at the just exterior part of the wall, it might not all be exactly the same temperature. Why is that? Well, I mean, some parts of the wall, there might be, um, parts that are more filled than others. And so there's a little bit different capacitance at different points along the wall. And so I have a lot of different temperatures. We can look at the lumped average, right? We can just take an average of that. And that's really what this part is about, is just simplifying it. So instead of doing partial differential equations, because we don't solve them in this class, we're going to lump them. So basically, I can look at just a single average temperature. And I can break it into, 2 parts or 3 parts or 5 parts if I want to kind of look at different stages. But ultimately, we've got to simplify things. So we're just going to lump things together and just imagine they have one average temperature. So now we get to the elements part. So we'll talk about that a little bit and then how we can set up our stuff. The 2 elements that we're going to cover are thermal resistance and thermal capacitance. Do you know any name for like a material that's good, that has a good thermal resistance? Huh? Yeah, insulation. So if you have an insulator, that's there to limit the amount of heat flow. So that's what we'll talk about. So you probably know this from way back in different science classes you've had. There's 3 different types of heat transfer: conduction, this is diffusion through a substance; convection, where you have to have a fluid transport; and radiation. Now, for the first 2, we're not even going to cover radiation. That's nonlinear. We don't like it in this class. For the other 2, there's a linear model. So again, if I'm looking at average temperatures, everything like that, heat flow rate, Q, is equal to basically delta T, whatever that temperature difference is, divided by R. So if R is infinite, we're not going to have any heat flow. That's a really good insulator. What does this equation look like? So the answer, oh, I'm excited. No? What? What? Yeah, it's Ohm's law. It's Ohm's law. Remember we talked about it for a resistor, like a valve for hydraulic? It was delta P over R. Yeah, so the R kind of gives it away. It's like a resistor, right? This is a resistor. It's insulator. I'm right. We have 8 people. Look at that. I was right. I guess 8 people today. Okay? So there's still time to, yeah, there's still one time. Okay, guys. So this is basically Ohm's law, where I have delta T over R. So again, very similar equations. It's linear. It's nice. So this is on the equation sheet. Q is equal to delta T over R. Now, if it's convection or conduction, that's where we see what is that R value, because the R value changes based on which type of heat transfer we're talking about. So on this slide, if it's conduction, R is equal to X over K, which is the thermal conductivity coefficient, times the area. You can get these K values on Engineering Toolbox. You can ask ChatGPT. Maybe they'll give you the same answer. Maybe. But I can find these values if I know my area and I know the thickness. I know what the resistance is from one end to the other. And so from there, we can kind of calculate our heat flow. So for example, copper has much higher conductivity. And so it's a really good conductor for insulator if I'm using convection. So anytime I'm using air, If air is a part of it, that is a fluid transport, right? If I'm using water, whatever, oil, I want to use convection. So this is slightly different. We do involve the area, so the area of contact, but then H, that would be the convection coefficient. So for example, water has much higher H than air, so therefore air is a much better insulator. And then again, like I talked about, we're not going to cover radiation. It's nonlinear. Usually it's just not very large compared to the other types, right? Conduction, convection, I get pretty good heat transfer. So we're going to just disregard it for this class. I was really bummed about that. All right, ready? Those are again, Ohm's law. Delta T over R gives me my heat flow. Lastly, capacitance. It's a measure of the ability to store heat due to its mass and thermal properties. So capacitance is just the mass of that object multiplied by its specific heat. So the more mass I have, the more I can store, right? And then obviously some water, much more capacitance than air. So we can store a lot more heat in that, right? Questions? Those are like my two elements: capacitance, resistance. And then from there, I'm just looking at, okay, let me model it. I've got a box. What's coming in? What's leaving? And we can try to figure out what the temperature is, because that's our goal, is figure out what will our temperature be as a function of time. When will we reach steady state, so forth. Now, before we do a problem and then take a break, if I had, let's say I'm talking about the wall again, and maybe not this wall, maybe like a wall at a typical house. If I've got, let's say this is like the exterior wall, this is maybe the insulation, and then this is like the wood. Each of these is a slightly different material. It has a different thermal conductivity. And what would happen if I wanted to model all of this? Well, if I wanted to, let's just say, figure out the temperature difference. If I know the outside temperature, let's say T ambient, and I want to figure out the internal temperature, what could we do? Well, we could take, one way that I could do it, I could actually draw it like a circuit where I have my resistor. We could call this R1. This is R2. This is R3. So I've got my outside temperature, I've got my inside temperature, and then we can just kind of find the flow, the heat flow going from one to the other. So I could figure out all these different resistances, because let's say for R1, that would be X1, the thickness, over its conductivity times the area, where all three of these should have the same area. But there's a problem with this. There's a problem with this. It's going to give me somewhat decent output, maybe, depending on what these properties of materials are. But the problem is that this model doesn't include each material actually storing energy. It's just saying none of these are storing energy. It's going from one to the other. It's really not a very good model. So how could we model it a little bit better? And you don't have to use a circuit. I mean, I could draw three boxes. Each of them has a capacitance. So there's a C1 here, there's a C2 here, there's a C3 here. And then there's going to be different flow rates going between them. I could call this Q1, Q2, Q3, Q4, depending on the resistance between them. But how do we determine this? I'm going to draw it like a circuit because I think it helps. Let's say this is T outside temperature. I want to figure out the temperature of the first material, but where am I looking at the temperature for the first material? Am I looking at the outside? Well, that's TA. Am I looking at this? Should I say that this point right here, this is my temperature of the first material of the brick or whatever? What would you say? What's a good temperature I should use for the brick? What? X over 2? Oh, delta X over 2. Split it in half. Absolutely. So instead of just looking at one side, I can split up its resistance by 2. Yeah, so we're going to cut it in half. Now I can get a pretty good average temperature for the brick. And the brick is going to store energy. So this can be my first capacitance. So some of the energy is not going to go all the way through. Some of the energy is going to be stored in the first material. And we're going to model that at the middle of the material. And then half of it is going to, from one edge to the middle, we just split R1 divided by 2. That R1 equation is still the same from up there. And then from there, we can break this up again. So now I'm looking at material 2. I want to find temperature 2. So we're going to take its resistance over 2. And then we get to our third material. It's also going to store some energy. And we want to find that nice average temperature. So this is a nice way to look at it and make sure that we're not forgetting materials do store energy. What temperatures are we looking for? They're at the middle of them. So this would be my Q1. This would be Q2. This is Q3 and Q4. So to get a nice average temperature for each material, you want to break it into 2. How many of you already took heat transfer? Oh, did you use circuits? Okay. So yeah, this is a way to kind of visualize it, break it up. It can be helpful, and the equations are really similar. I don't have to do KVL and stuff. I've got the equations, but just knowing this flow rate is actually a combination of these two resistors, R2 over 2 plus R3 over 2. That's really the resistance going from the middle of this material to the middle over here, because we want to find temperatures at the middle, a nice average temperature. Questions? All right, we're going to do a problem. I'm going to show you kind of how to use both body, then we'll take a break, do one more problem, and then finish with an activity. So how to model these. This is the equation that's on the equation sheet. This is what we want to use. So if I have mass flow rate coming in, if there is a fluid coming in with its own temperature, that's where we're going to use these ones. If something's flowing out, same thing. And then anything that's strictly just heat, that's my sum of Q ins minus sum of Q out. So to get this model, I'm going to have, again, our output that we care about is the temperature. How is it changing with respect to time? What this means is that for every capacitance, every body, I'm going to have one first order equation. Just like with hydraulics, just like with circuits, every capacitance gives you one first order equation. So, you got it? It's on the equation sheet. And let's do example 4.7. So figure 4.18 shows an interior office room with a baseboard heater Is it a gas power? Anyone grow up with like a gas, like a baseboard heater? Like those big heaters that are by the window? Nobody? Oh, old houses. Uh, we're dealing with an interior office room. I've got the heater, and we want to figure out what the temperature is going to be like in that room if we run that heater for a long time. So our goal is to derive the model of the thermal system. Now there's two figures, but really it's the same figure, just two different views. So this is the top view of that room. Each wall has a slightly different resistance because, it's got doors, windows, but we can lump it all into one resistance. And then we're also showing the ceiling also has resistance in the floor. Now, is the room that we are in, does that match kind of what we're dealing with here? Interior office room? Is this an interior room? No, we got an exterior wall right there, right? Okay. So the reason why that's important part of this is because, if I'm in an exterior room, like right outside that window, temperature gets a lot more different, right? If I'm in an interior room, we can just say that all of the other temperatures are about the same ambient temperature, right? So whose office would you say this could be modeled? You've been to some people's offices. Most of you haven't been to mine. I'm on the outside of the building, so it can't be mine. Whose office could this be? Does anyone go to any office towers? Bullock's on the fourth floor. Can't use Bullock. Bruce Lee. Anyone go to Bruce Lee's office tower? Collins. He's right across from me. Okay, so Collins, Crick, Bruce Lee. They're all interior office room. They've got their four walls. They've got their roof, their ceiling, but around them, we're just going to say that it's all the same ambient temperature. Now, if you've actually been into our offices, you're going to notice that some of them are a lot colder than others. So this isn't really true. But here we go. I've got a heater. I've got around this whole room, all six sides, we're going to have the same ambient temperature. Each wall and ceiling and floor has a slightly different resistance that includes the windows and doors and whatever. So we can just lump them all together as one resistance. I don't have to model every single part. They're giving us R1 through R6, and our goal is to find the model. Okay, I think we're on the same page. Let's do it. Take a breath. What would you say the order of the system is? It is. I have one capacitor. One capacitance, so I'm looking for one first order equation. We are trying to find temperature. How does that temperature change of the room as a function of time? When will it get to 100 degrees Celsius? It's killer. Okay, one first order equation, that's good. Great. Next up, body diagram. Now, you don't have to be too fancy on these. You can do the same as kind of hydraulics. I'm just going to draw my boundary here. So we have a capacitance of the room and we have a temperature, and that temperature is changing. Capacitance is a function of the volume. And the baseboard heater is providing a heat, QBH. That is, now, this could be gas, it could just be electric. A lot of, actually, professors have a lot of plug-in little heaters, okay? So in Arizona, what's going on? Anyways, we're pretending it gets cold. Wait, what? It's cold? I don't know, this morning wasn't too bad. But we've got these electric heaters, so it's taking electrical energy, it's turning into thermal energy, and we are inputting it into the space. So I've got heat flow coming into the room. Is that it? Are we good? Why not? Heat is leaving. So as I heat up this room, look, we can all start at the same ambient temperature, but as that temperature rises, as I get more of a delta T from one side of the wall to the other, that's where we're going to see that heat flow out. And so we want to model that for all of them. So there's going to be a Q1 across R1. There's going to be a Q2 across R2. It's going to be a Q3 across R3 and a Q4 across R4. There's also a ceiling. So we'll do a Q5 and a Q6. Oh, lots of ways it's leaving. We got 6 different directions that the temperature, that heat flow is going to go. And we want to make sure we model it. If I don't know which way the direction goes, you just pick one. Just like with a spring, you just say, hey, I'm saying this one's greater than the other. So we're saying that the internal temperature is greater than the ambient temperature based on the arrow directions, right? And that's going to play a role in my definitions once I get there. Questions? What? Oh, no. Okay, that looks good to me. Now we get to inputs, outputs. The input, the count of 3, 1, 2, 3. Yeah, Q, BH, the baseboard heater. And the output on the count of 3, 1, 2, 3. Temperature, yes. Not Q1 through Q6. What we care about for the equation is what is the thing we're tracking, what is changing over time, and that is temperature. Just like pressures for hydraulics, yeah. We are modeling the heat loss for the doors and windows. Those are all lumped together into each wall's resistance. So like R1 is going to be less than R2 because it has way more ways for that air to leak out. Now, one thing we didn't mention was under the doors, typically there's a little crack, and that means that air can pass in and out. We're going to say it's well-sealed door. So we don't actually have to deal with like enthalpy rate change in that case. There's no M dot in or out. Okay. You know what? Let's go back to that. It's no M dot. It's all sealed. Okay. So we know our inputs, outputs. Now we get to our definitions. Now the first one I want to use is what I showed a few slides ago, and this is on the equation sheet. And I always just start with this because it's on the equation sheet, and then we can simplify it from there. So CT dot is equal to sum of M dot CPTN M out dot CPT out plus sum of Q in minus sum of Q out. Now this looks pretty similar to hydraulic. It's just we have 2 different parts. The first 2 parts are if I have mass flowing in and out. They have different temperatures. That's going to change my temperature inside the capacitance. Then the other 2 are just strictly heat. Anything we can cross out here? We just talked about it, yeah. Yeah, we don't have any mass flowing in or out. As for Q ins, that's just going to be my base heater. And so really it's just what the Q outs are going to be. So Q off the equation sheet, this is Ohm's law basically. Heat is equal to delta T, change in temperature over resistance. Another question that's always been asked, which is a good question, is do I use convection or conduction on this? Convection? What about the thickness of the wall? So in this case, they gave us R1 through R6. R1, this could be a combination. It could be like the convection plus conduction. So each of these R's, R1 through R6, could just be a combination because it's like I'm just adding them in series. I have some convection resistance as it goes to the wall. There's conduction as you go across the wall. And then there's convection as it goes to the other ambient temperature. So I don't have to use it. I don't have to change these into X over Ka. All I'm going to do is if the problem gives me an R value, I'm just going to use that R value. Does that make sense? So they want us to use R1 through R6. That's what we're going to use. We don't have to try to figure out what those values are. They're just given. And so, for example, Q1 is going to be delta T over R1. What should delta T become? What? We're going from high temperature to low temperature. High minus low, and that should be what two temperatures do we have? Start there. T and TA, T ambient. So which one's higher? Which one did we show on our diagram to be higher? What? Yeah, T. So we're going to have temperature of the room minus ambient temperature over R1. And really, we can just use this for all 1 through 6. So I is from 1 to 6. I've got 6 different resistances. They all have the same equations. So we'll be able to combine them at the final part. So I'm going to take this starting equation. We're going to put in our Qn, which is just the baseboard heater heat. We've got our different outputs, 6 different outputs. And then from there, we should get one first order equation. Questions? Okay, so here we go. Here's our equation. Sum of Qn, which is just baseboard heater, minus the sum of all of the different heats. So we have 6 different heats right there. And so this is going to be like T minus T ambient over R1 plus all the way to T minus T ambient over R6. So we can rewrite this as baseboard heater minus, we've got a T minus T ambient times the sum of 1 over Ri. So we're going from 1 to 6. all those different values. The last step I want to do is I want to get all the T's to the same side because this temperature is the temperature of the room. It's the same as the CT. This is the temperature that we're trying to track. How does it change over time? And so we get a CT dot plus temperature times, this is where we have the 1 over R1 plus 1 over R2 plus 1 over R6 is equal to the baseboard heater temperature plus T ambient times the same thing. And that is our first equation, our only equation. It is first order. I cannot create a transfer function unless the ambient temperature we can set at 0, which would be pretty cold, especially if it was in Kelvin. So I do have this first order equation where if I know what this heat flow is and I know what this temperature is, and they gave us all these different resistances, we should be able to solve for the temperature, like what time is going to reach until it reaches a steady state. How hot can this room get before someone complains? Questions? Okay. So we're going to do a problem after the break. Let's take a break. It's 8:15. Perfect. Come back at 8:20. We're going to do one last problem, and then we'll do an activity. We got hot chocolate, tea, everything like that, hot water. So we'll do it soon. Maybe 4. But everyone will just keep living life, just hands and let's go, right? Not our problem. Okay, we're gonna do one last problem, then we're gonna do an activity. But let's see if this, nope. Okay, here. What? Is there just too much stuff on these slides? What's going on? Great. Okay. Did you catch that? My goodness. Wait. I'm gonna freeze it. I'm not even on that slide anymore. Okay. Figure 4.8 or example 4.8. This is a double pipe heat exchanger. So this is our last problem we're gonna do today, and then we're gonna do an activity. Here's what's happening. I kind of put it in red and blue. This is a heat exchanger, which means I'm taking a hot fluid and I'm transferring some of that heat to the cold fluid, especially for making sure we don't have too hot of oil in the car or whatever. So both of these flows are steady. So this is my input to the hot. So it's got a pretty high temperature going in. It's got a mass flow rate. It goes through here. It gets cooled down a little bit. And then it gives us an output temperature of T1. It says that both flows are steady. So that means that the input mass flow rate is equal to the output flow. We're at a steady state, a nice constant movement. So that's not changing. Then I've got the cold temperature. That comes in with a pretty cold temperature here. It flows through with its own flow rate. And then it warms up a little bit and gives us an output temperature of T2. And we want to find the mathematical model of the heat exchanger. Two important things that I underline. We're going to say, which is, again, when you're talking about heat, you've got distributed temperatures. It's not all the same. But we're going to simplify. We're going to say that T out, this output temperature is the same as the average temperature T1. So it cools down a little bit. That's my average temperature. That's what we're going to model it as. Same thing for T2. It warms up a little bit. It has a temperature inside T2, and that's what the output is. That could be quite an approximation, but we're going to use it that way. So first we're going to breathe. Then we're going to identify the order of the system. What would you say the order of the system is? It is second order. How'd you get to that? Yeah, there's two capacitors, right? One surrounds the other. So we really have like two different control volumes. So therefore, we're going to have two first order equations. One of them is going to be the T1 dot. So that's going to be one first order equation. The other one is going to be T2 dot. So I'm going to have one equation for each. And they definitely relate to each other, right? There's some heat passing in between the two of them. Okay, now we get to body diagrams. This is where I'm gonna give you a quick schematic, and then I want you to fill in some of what's going on here. Okay, so I'm gonna say that this is. So we're all on the same page. I'm gonna draw it as two boxes. I'm gonna say that this is the inside temperature, and this is the outer temperature. And yeah, I'm gonna leave you at that. So I've got my two different tanks. This is the inner shell, this is the shell. Sorry, what? No, this is the tube. This is the shell, T2. And I want you to identify what are some of the inputs and outputs. And because it is a heat exchanger, I'm just going to give you this hint. There should be an arrow going between the two. But we want to figure out all the different inputs, outputs, what's going on before we set up our definitions. And if you got questions, just let me know. Or equals T. Just as a reminder, the flow rates are all equal throughout the two. The temperature outputs on it. That's a good question. I think you got a good job, you know? Good arrows. Good arrows happening? Nope, everyone's just waiting for me to do it. Great. Well, I gave him a good try. Um, there are arrows in the diagram, are there not? Right? So, what do these represent? Let's look at the hot fluid, the tube. Does the temperature change based on those inputs and outputs? The answer is yes, because I have fluid coming in. So that's going to be it has a m dot, it has a fluid capacitance, and it has an input temperature. So it's coming in pretty hot. It'll cool down to T1, and that's what the output is going to be. But it's, again, the same flow rate. It's just going to be T1 on the output side. Is there any heat happening into T1? So that was the fluid, which is bringing mass and temperature. Is there any just heat happening for T1? Anything? It just comes and it goes, and somehow it loses heat. Yeah. Wait, what? Say that again? Beautiful. There's going to be a flow. I'm going to call it Q1. That is the purpose of the double pipe heat exchanger. It is going to take heat energy from tube 1, and because of that large temperature difference, it's going to flow to T2. That's why they like to surround it, get as much surface area as possible. Give us that. Now, in this case, they gave us a thermal resistance of R1. So this is across, you can say R1 is the boundary between those two. And that, again, could involve some of the convection, conduction, getting to the wall, getting through the wall, getting to the other fluid. But we're just going to use that R1 as the total resistance. And now for T2, this is the shell. It enters with its mass flow rate. It has a starting temperature, which is pretty low, and then it exits with the average temperature T2. So obviously T2 is going to be larger than TN2 because I'm getting this heat coming in. Is there anything else that we might be missing? Maybe look at the diagram. Yeah. Wait, say that again? Heat out of T2. Yeah, because the shell has a thermal resistance R2. So there's going to be another flow out of there. Again, you can name these whatever you want to, but looking at the problem, I have two different R's. Therefore, I should have at least two Q's. Then for each one, I've got an input mass flow rate output. All right. So part of these problems, and you do have two thermal problems on the homework, okay? It's just getting a little bit of practice. Let me draw the body. Let's identify, is there any fluid coming in or out? If not, great. I can just use Q's. But there's always, especially if there's an R. In this case, I've got two R's. We should have two Q's. So take your time on it. Just try to identify everything. Because then when I get to the final part, I want to make sure I've got everything I need to sum. What is being subtracted? I'm saying T1 greater than T2, right? So what's negative for one equation is positive for the other. Questions? You all had that. I know it was just in your heads. You were just waiting for me to just like put it in. Yeah. Okay. Cool. Next step. Inputs, outputs. Again, I'm going to do tic-tac-toe because I've got two different bodies here. This is in, out. So we've got the tube, and we've got the shell. What is the input, you would say, for the tube, the hot fluid? What are some of the inputs affecting that? TN1. Absolutely. And what would the output be for the tube? T1. And then for the shell, the output is going to be T2. So what that means is that For our equation, we're going to have a T1 dot for the first one. We're going to have a T2 dot for the second one. We're seeing how the temperature changes as a function of time. What is the input for the shell? Tn2 and T1. Wait, did you say something else? Wow. Yeah, that affects it. Is the tube affected by anything? Maybe they affect each other, right? The colder that temperature, it's going to affect my temperature. You know, I forgot on this part here that heat is leaving to some kind of ambient temperature. So I didn't actually specify it on the diagram, but there's an ambient temperature that we want to put. That is also somewhat of an input. That's going to affect that shell temperature. So ambient temperature, we could also list here. And again, this is not the most important part of this, but trying to figure out for my equations, you know, what's on one side, what's on the other. And they are in fact affecting each other. That's what the heat exchanger is all about. Okay, questions? Next step, definitions. First off, we're going to start with the equation that starts on the equation sheet. Ct dot is equal to the sum of Mn dot times specific heat Tn minus sum of M out dot specific heat T out plus sum of all Q in minus sum of all Q out. Now in this case, you know, the last problem we had, there was no air flowing, nothing flowing. In this case, we are going to use all four of them. I think at least three of them. Let's define a couple things. First off, M in dot 1 is just equal to M1, which is equal to the output. Same for mass 2 dot. So there's no difference between the input flow rate and the output flow rate for both of those tubes. One thing that they specified, which I'll just write again, is that T out 1 is just going to equal the average T1, and T out 2 is just going to equal the average T2. Now, in my diagram, I had two different Qs. So we had a Q1 and we had a Q2. And so we want to define them. Now, both of these are going to be the same starting definition. It's delta T over R. In this case, we have an R1 and an R2. So it's always that. If it's convection, conduction, same equation. They just gave us an R value, so we're going to use it. What should Q1 equal? Sorry. T1 minus T2, very good. Because those are the temperatures it's flowing from high temperature T1 to low temperature T2. Yep. And again, this is similar even to hydraulics, right? I have a resistance between the two. I have a flow across the resistor. It is going from high to low. So that's my delta T. I'm always going high minus low across the resistor. Q2 is equal to what? Delta T. What is that delta T? Yes, T2 minus T ambient over R2. Very good. So now I've got my definitions. I kind of know what's going on. We're going to start with the first one with the tube. We can set up our equation, and then we should end up with two first-order equations. A lot of variables similar between the two. Questions? Okay, so let's start with the tube. So for the tube, that means that I have a capacitance. What is the capacitance of that tube? We can look at mass and specific heat, or depending on the volume, what that is. But here's my first order equation. It's going to be, I've got M1 dot, that's my input, times specific heat, times the input temperature, which is Tn1, which is pretty hot. Then leaving it, I have the same mass flow rate, same specific heat, and we're using the average temperature of T1. I do not have any input heat flows, but I do have a Q1 leaving there. And so if we wanted to, we could combine these. This is going to be Tn1 minus T1 minus, this is going to be my T1 minus T2 over R1. So a lot of it comes down, just like with mechanical circuits, just like how good is your schematic, how good is your diagram. If you've got everything labeled, if everything's like pretty clear, it should be pretty easy to set these up, knowing what my inputs are and my outputs. Next step for this one. That's done too. Next step. Yeah, let's get all the T1s to one side, right? That's a good idea. So I'm going to add all the T1s to one side, so I get C1, T1 dot plus M1 dot specific heat T1 plus 1 over R1 T1 is equal to M1 dot specific heat Tn1 plus 1 over R1 T2. And I always just like to get rid of these fractions, so multiply both sides by R1. We can get a R1 C1 T1 dot plus, I can combine these. So I get R1 M1 dot specific heat plus 1 times T1 is equal to R1 M1 dot specific heat Tn1 plus T2. So I just multiplied everything by R1, got rid of some of those other fractions. And now I've got a nice first order equation. Now you might be looking at this going, wait a second, we got two different dots here. I don't really like that. Well, the mass flow rate, m dot, that's a constant. Once we've reached a steady state with that, that's a constant. So that even though it looks like a derivative, it's not actually changing. That's just kilograms per second. And we're at a steady value right now. So it's not a big deal. So that's our first equation. The second one is very much like it. We've got C2, T2 dot. Just make sure you always have those. As I'm setting up the second problem, we got M2. And really, I can do the same here. It's going to be a Tn2 minus T2. In this case, I have a plus Q1, and then I have a negative Q2. So I've got one heat coming in, one heat leaving. So just rewrite this again. We've got T1 minus T2 over R1. And then what's leaving is T2 minus T ambient over R2. And so just like with the last problem, I'm going to bring over all the T2s, and all of them are negative currently. That's great. So I'm going to add them to the other side. So we get C2 T2 dot plus, got an M2 dot specific heat plus 1 over R1 plus 1 over R2 T2. This is equal to M2 dot C sub P Tn2 plus 1 over R1 T1 plus 1 over R2 T ambient. And the last thing I would probably do, just like with the one before, is try to get rid of all these fractions. Because if I ended up, trying to be able to create a transfer function, in this case, we couldn't really create a transfer function. We could do some combining, but I could multiply by R1, R2. I get R1, R2, C2, T2 dot plus R1, R2, M2 dot specific heat plus R1 plus R2. And that is my second equation. Oh, again, don't worry about the M2 dots. That's just a constant. So we have two first order equations, one for T1 dot, one for T2 dot. We could make some, if I put in the S domain, I could make some substitutions. I could cancel out one of these if I don't care about either T1 or T2. If I really just care about T1, we can put it in the S domain, manipulate it just to get one equation, looking at what is that temperature of T1. That is possible. But in this case, I'm just going to leave it at the two different equations. Questions? Again, process is very similar to hydraulics. I have a capacitance, therefore I have a first order equation. You identify what is the input flow, output flow. And so that's just like with that one, that's Cp dot, pressure, how the pressure is changing. This one is capacitance times temperature dot. How's the temperature changing? So just using that equation sheet, you don't have to memorize anything. It's just identifying inputs, outputs, following your diagram, and then getting one. And it should always be stable. The output side should be stable, like both of these are, which means all positive on the output side. Questions? No questions? Okay, I got one last activity. Here it is. And I will post these slides. The thermal activity is we're going to model this in SimScape. So if you can pull your computers out. Did anyone bring a cup they want to fill? Or I got some of these styrofoam ones. Styrofoam. Now I'll just make at least one for each table, but I do have hot chocolate. I got different teas in here. I even got the spiced apple cider. Yeah, it is pretty good. So if you want your own cup, I got some. I'll make some here. we're going to model this in Simscape. So in Simscape, you want to pull up a thermal. You're going to create from a thermal template. And so by the end of this class, in half an hour, you should be able to have something that sort of works. But our goal is to model the cup. So thermal, just a regular thermal template in Simscape. Our goal is to create the Simscape model. The first thing though, I need to figure out, we're actually going to model, we're going to try to match what's going on here. So I've got hot water I got from upstairs. Not upstairs, okay? Got hot water. I'm going to pour cup into each of these. Oh, that was a little fast. Okay. And I'm going to take the temperature. The temperature is 161 degrees. Set 5-minute timer. I got a timer going for 5 minutes. Every 5 minutes, let's test the temperature. But you can use it better if you want. Or no, you don't care? That's gonna change some of the properties. Water's pretty easy. But what you're gonna want to look at is under relation library. You can look at the dimensions of the cup. I can get some calipers out. Like, I will just leave it. But the goal is to, and I'll show you my model student. You want to try to figure out, okay, I should have a thermal capacity. That is my water. Got styrofoam. So we've got our installation out. There is an open side to this. So it is directly contact